This is the software that we use. It's called Escape, and you'll see it's got, around the side there's various tabs. If ever you cannot find the part that you're looking for, it just means that the tab has been hidden. For example, you can hide the tab by pressing the auto hide, you can pop it back open by clicking on it, and you can pop it out by pressing the float. First, we need to check the pressure of the FlexiLock and the pressure of the analysis chamber. We have the mimic diagram for the instrument, and this tells us the pressure of the SAC, which is the sample analysis chamber. Basically yellow means it's under fine vacuum, which is good. In order to transfer a sample from the FlexiLock to the SAC, we need a pressure of about 3 times 10 to the minus 7 or lower. You can see now it's at 1.2 times 10 to the minus 7, which is good news. So we can now transfer the sample from the FlexiLock into the SAC. We click on the sample loader tab. This tells me that in slot 1 we've got the plain dual height holder, and slot number 2 and slot number 3 are empty. So we need to take a photograph of the bar while it's in slot number 1. I press move to camera position, and now the sample magazine will move underneath the camera that is in the FlexiLock. Move to camera position complete. I then press the play button to start the loader camera. It's got a live image of the sample bar, so you can see our coin, you can see the samples that we've got here. I then press stop loader camera, and that takes a screen grab of that. If we aren't very happy with the contrast, we can turn the light on and off, like so. We've turned it off. When I turn it on, it will be very bright and the contrast will be different to before, and then we can then save that grab, and I've saved that. So now you can see, if we go to here for the cameras, we've got 2 images of slightly different contrast, and these are what we can use to assign the positions. Now that we're happy, because the FlexiLock pressure is low, I press the transfer to sample holder to stage button, and the sample transfers from the FlexiLock into the chamber. Typically this will take about 5 minutes. If there's already a sample holder on in the stage, that sample holder will be dropped off first into the empty magazine spot, and then our sample holder will be picked up. So while we're waiting for that, we can set up an experiment data file to save our data. We go to the Data Organizer tab, New Experiments, and then we make a folder where we need. So as you can see here, we actually have cameras inside the chamber. So this is a good view. It shows us when the sample bar is being picked up. So we can see the sample bar is almost there, and the stage goes in, and it should engage. So sometimes when you do this, you will get a box come up that says select sample holder type. This is because the metal contacts on the sample holder might be slightly damaged or might not be in the position that they should be on, which is why it's really important to not touch the metal contacts when you're preparing the sample. So I just need to confirm that this is a plain dual height holder, and once I press OK, the system will carry on. So once this gate valve closes, then we're good to go. Transfer sample holder to stage is completed, so we don't need this window anymore, so we can just minimize that one. So what we do need now is the analysis location window. And this is where we set the points for analysis. It uses the image that we have taken here. To add a position for analysis, we press on the point here. I'm going to call this powder. To add a point, I just go to the image and I left click, and it sets a position for me. So I've got M1, which is on the grey powder, and M2, which is on the purple powder. I'm then going to press add. I'm then going to do the same thing for the coin, so I'll go down here, call this coin, and I'll do the same for the foil as well. The bit that we need to remember is that this image, it might be a few millimeters off the true location. This is just a photograph. I click on the positioning tab and I press display microscope. So you can see here, this is actually a live image of where the red spot is there, and we're at 2 times magnification. I'm going to go to M1, I click just in the box on the light blue, and then I press the move to location, and we move to that location. If I press the turn crosshairs on and off, you will see that this is the true location of the sample. We can fine tune the position just by using these controls down here. At the moment we're at 64.929 mil. And if I press the plus, we will move 1 mil to the right. If I press the minus, we'll move 1 mil to the left. I'll then do the same with the Y. I'll move down a little bit. we can see that the image isn't really in focus. It's important that it's in the right focus, so I'm just going to change the Z height by -1, and now that's got a little bit sharper. That's good to go. So I'm going to update the location, and that will save these coordinates for me. I'll then go to position 2, and I'll just move down a little bit, and I will change the Z to -1 just to get it into better focus. What's important to notice that when we change the Z, it appears that the X-axis is moving. And this is because the camera is aligned onto the X-axis. We aren't actually moving left to right, we're just moving up and down. So I'm just going to move back a little bit just so we're in the middle and update the location. And the coin is a lot thicker than the tabs, and so this will be a little bit blurrier. I would estimate that we need to probably go down by about 3 mil for this one. So you can see now it's starting to get into focus here. That's good. So we're now in focus, we're on the Queen's neck, so that's probably a good place to stop, so we'll update that. What we do is we'll go back to position 1. We can open the acquisition methods window. If we open the folder here, there's a few different methods that we have that are set. What we want to do is we'll do an auto Z first, and that will set the height of the samples. So in the experiment, I'm going to say that save all of this data in the test folder that I've just made. And you'll see here this box is ticked. This is for the charge neutralizer. So typically we keep the charge neutralizer on unless we've got a purely conductive metal sample. If there's any chance that there's a non-conductor in there, it's always good to have the charge neutralizer on, and then you can charge correct afterwards. So what I've done is we've gone to position 1, I press the blue arrow, and that will submit whatever acquisition method we had set up, it will submit that. Back in this window we've listed the 3 here, and I just need to tell it to start. Auto, and then start. Each of the scans is estimated to take 2.5 minutes. We'll stay with the instrument while it's happening. When it first turns on, it just takes a few minutes to warm up. We're actually moving the sample up and down, and it's trying to find the optimum position. We move up and down by about 1 millimeter each, and then we do a fine tuning. And where the signal is the highest, we set as the position to analyse. That's set that up, and it's going to update it any second now. So that's the optimum. So we'll then go to sample number 2, and we'll do the same thing. And what's important to note with the crosshairs is that you can see we have a scale at the bottom. So as long as the sample is within this middle circle here, we should be okay. With the coin now, we're just doing the last auto height for that. It looks like we're moving left to right, but we're not. We're actually just moving up and down in 1 millimeter increments. But because the camera is aligned onto the X-axis, it looks like we're moving left to right. And we're almost finishing now. We're just doing the fine tuning, and this is finding the optimum height for us. If you've got a very flat sample, this is a lot easier than if you've got a bumpy powder sample. So the flatter the sample, the better. So we've now finished all the auto heights. So I'm just going to close the microscope. We don't need that anymore. And I'm just going to bring the analysis position back onto this window for us. So I'm just going to make this a little bit smaller, just so we can see everything. So when I go open method, there's a high power method and a low power method. So if we've got a solid metal sample, it's important to use the low power method just because the signal will be very strong and it might damage the detector. With powders and non-metal samples, it's okay to use the high power, but if in doubt, always use the low power first. So I'm going to use the high power method for this one. So we just want the survey high power acquisition, but this is all the parameters here. We don't need to change these. And then I'm just going to submit location for acquisition for M1 and M2. And then I'm going to close this tab, we don't need it anymore. This will take 2 minutes to do for the scan. It will then move on to the second powder, and then we'll see what we get. While it's acquiring, we can look at the counts per second on the left-hand side. Typically, we want a background less than 300 times 10 to the 3. If we get a spike, we want the spike to be less than 1 million. If it's higher than 1 million, you need to stop the analysis and do the low power method. So to stop the analysis, you just press the stop button here. Once this has finished, it will turn blue. If I double click on the white scan here, it will open up the file that we've just had, and I can now analyse the peaks and assign the peaks for this. So there are 2 different ways to do that. Firstly, we can do it the automatic way, so I'll show you that first because it's a little bit easier. We want to open the data processing tab, and we want to convert from ESCA spectrum to peak ID. I then just hold and drag, put it into this box, press the process button, it does a bit of a spin, and then we press the display items results. And it very quickly analyses the data and it shows me what we've got in this sample. This isn't 100% accurate though, so you have to use your own intuition. We can see that there's cobalt, oxygen, nitrogen, sulfur. There are a few peaks that it hasn't picked up, so we'll do it the old-fashioned way and we'll see what we get. We just open it up and then we click on this Add Element Lines button, and it gives me this red bar at the bottom, and at the moment carbon is selected, so it shows me where the peak for carbon 1s should be. So if I double click that, it will lock it into place with a green. And then here I can just type in a different element, so I'm going to type in O for oxygen, and it shows me where oxygen should be. So we should have an OJ feature there and a 1s feature there. So the oxygen, we've got the 1s, let's type in N for nitrogen. So yeah, we've got a nitrogen peak there, and cobalt, CO. This peak I know from experience that it's sulfur, so I'll type in S. You can see there's a peak here, we're not really sure what it is. If we just hold the mouse underneath and draw a line, when I release this, it's going to show me every single peak that could be there. So it's going to get quite messy, but then we can just work through it and decide what it actually is. So I've clicked on samarium, and we see that if samarium was present, we should see a doublet here, which we don't. So I'm going to remove that by double clicking. Praseodymium again, we should see other features. We should see a doublet down here. We should see big 3D there. We get rid of that. Bismuth again, no, we don't see the doublet there. Get rid. Xenon, again, we'd see more. So it's either fluorine or iridium. Iridium, no, we'd see other peaks. We'd see a doublet here for D, and we'd see a stronger peak here for F. And if we look at fluorine, for fluorine, we'd expect a single signal for 1s and an OJ feature here, which is what we see. So we've correctly identified that as fluorine. So now I know that this sample contains oxygen, carbon, nitrogen, cobalt, sulfur and fluorine. So now I need to perform high resolution scans of these elements. So to do that, I go to the acquisition tab, open methods, and open the high res methods. High res 10 mil acquisition. And then I just type in the elements that we want. So already oxygen, carbon and nitrogen are pre-populated, but I want cobalt. And if you're not sure which cobalt peak to use, we've got a trusty periodic table just here. So we just have to go to this and it will tell us what we need. So for cobalt, I know that it should be a 2p. Press enter and it gives me some parameters already filled in. So then what I have to do, I just have to check that this is correct. Using the magnifying glass here and the middle mouse button, I'm going to zoom in on the cobalt peak just to check that the numbers here are correct and that we don't need to change the region a little bit. So it says 810 to 773. So 810 is here, 773, we're going to miss a little bit of it. So just to be on the safe side, I'm going to bring this down to about 760. Press enter. I'm going to zoom out by pressing the middle mouse button. So we've got sulfur, 2p. Again, I'm just going to zoom in on the sulfur 2p. So 172 to 158. Again, it's a little bit shifted, probably because the sulfur is ionically bonded, so it's shifted quite a bit. So we'll bring it down to 150 just to give us a little bit of background. And finally, fluorine, F1s. So with the fluorine, again, it's only small. So zoom in a little bit more, 695 to 675. Again, we'll just bring it down a little bit. So here we have the auto quality box, so I'm going to tick this. So what that does, it will do a maximum of 5 sweeps, but if the signal to noise quality is reaches this number before 5 sweeps, it will stop after that number. So that means that we get high quality data, but we're not wasting too much time. So for example, we have a very strong nitrogen peak. So even though we've ticked the box here for 5, it will probably complete in 1 or 2, it doesn't really matter. But with that ticked, it just ensures that we get the best quality that we can. If you are a little bit worried that you haven't got a very strong signal, you can change the 5 to 10, and that will just do 10 sweeps and we'll get better data from that. So now this is good to go. So I go back to the analysis window, and I'm just going to submit this for acquisition. So whatever is active in the acquisition method window When we press submit, it will submit it. We've now gone to position number 1 and we're acquiring that, and it should take about 35 minutes. It might be quicker if we don't use the maximum of 5 sweeps for the samples, but we'll see what we get on with. While this is running, we can now analyse sample number 2, the other powder. In the comparison tab here, I'm going to drag in sample 1 and then sample 2. Blue is sample 1, red is sample 2, and even though these samples are very different in appearance, they're actually chemically very similar. So the only difference I can see is that there isn't sulfur in sample number 2. All the elements are the same and their positions are the same, or very similar. So I go back to the acquisition methods tab, and I'm going to use the same template here, but we don't need sulfur. I can either delete it here or I can set the sweeps to 0. I'll just delete it. And then I'll go back to the analysis location and I'll submit sample number 2. So now we just have to wait for the analysis to finish. Now we have finished acquiring the data. So we can see on the left-hand side here, we've got the powder samples, M1 and M2, we've got all of the data. So we can now convert this into a VAMAS file and export it from the instrument. We go back to the data processing tab, and I want to change it from an ESCA spectrum to a VAMAS exporter. I can then drag all of the files into this box. So if I hold and drag powder, it will then bring me my powder samples from M1 and then from M2. I then need to find a place where to save this. Then press the process button and then the save button. Now we've created a VAMAS exporter file for this, and we can just check that the data looks okay in the CAS or XPS. And there we go, we've now got the data. So we're now going to analyse the coin sample. So previously we set the height, and now we're going to do a survey scan on this. I said before there's the high power and the low power. It's very important that we use the low power first because it's a metal. We're not sure whether high power will be too strong. Acquisition methods, open survey low power, and I'm just going to submit this for acquisition, and now we'll see what we get. I'm going to just do a quick peak ID on this. For ESCA spectrum to peak ID, drag it in here, press play, and display it. And you can see we've got a huge peak here, which is carbon. We've got oxygen, we've got a little bit of silicon, and it hasn't picked up anything else, which is obviously quite surprising because this is a coin. It's a gold coin. Well, it's not actually made of gold, but it's gold in colour. We should expect this to be made of copper, aluminium, but we don't see any of that. And that's just because XPS is a surface sensitive technique. So we're only seeing the top few nanometers, and this coin is very dirty. It's been in my pocket for a long time. Nobody takes cash anymore. What am I going to do with it? It's just been sat there. So I'm going to clean it up and we'll see if we can get any of the elements showing. We use the gas cluster ion source to clean samples. On the left-hand bottom corner, we right click and we go Instrument, Prepare Instruments, and it brings up this small box here. We then go to Mini-Beam 6, which is the type of GCIS source that we've got. And we need to tune it. So there's a lot of different parameters that we can use to tune it. Depending on the energy that we use, the cluster size, it can change basically the rate of cleaning. So as a rule, as a standard, we'll do the 10 keV, 1000 argon. So this means that the energy is 10 keV, and there'll be clusters of 1000 argon atoms. We'll change the raster size to 1, so we want the crater to be 1 mil by 1 mil. That's the area that we're rastering over. And then I press standby. It just takes a bit of time for it to warm up. When the GCIS prepares itself, the box turns on, but then also the argon line also opens. We'll see the mimic diagram change as time goes by. So it takes about 5 minutes. The argon valve is opened, and this just cleans the line. It evacuates any dead argon out. The sac backing valve is now opened. So now this part here is all under a rough vacuum. And once this is clean, that valve will close, and then the argon inlet valve will open, and the pressure will rise slightly in the chamber. And that's just because we have a very small amount of argon in there. So while we're waiting for that to happen, under the instrument in the control panel, this gives us the information on the progress of the GCIS standby mode. At the moment, we're at 81% complete, and it's taken 164 seconds to get to that stage. And at the top here we've got the sac pressure, the FlexiLock pressure, and the UPS pressure as well. So now you can see that the pressure in the main chamber is increased slightly to 10 to the minus 7 torr. That's because the argon inlet valve is open, so there's a small amount of argon in the chamber. To clean the sample, I'm just going to go back to the methods. I'm going to open a method called clean.acquisition. So for this method here, what it does is it does a survey scan, it then cleans the sample, and it performs another survey scan to let us see how well the cleaning process has happened. These are the parameters for the survey scan. They're slightly different to the standard XPS parameters, and that's because when we do any GCIS work, we do make a crater. To ensure that all the data is from the middle of the crater, we need to use a smaller aperture, just so we're not looking at the edges, because the edges might be slightly different. So we put an aperture in. So we do a 1 minute scan. We'll then do the mini beam 6, so this will be a 2 minute etch, and then we'll do another scan after that. So I'm just going to submit this. So you see this will take about 4 minutes, so it'll be a minute for the first scan, 2 minutes to do the etch, and then it'll be a minute for the final scan, and then we should get some better results. So as you're doing that, the instrument makes a bit of a noise, and that's the aperture and the iris going into place and changing the aperture. So I'll go back to real time here, and we'll just wait for it to finish. We've cleaned the sample, so we can look at the before and the after. If we go to the comparison, this is what it looked like before. So we've got a big peak here for carbon, a peak for oxygen, some small features down here, and a little calcium peak as well. Then after cleaning, you can see what a difference it makes. So the peaks here have shot up, and we've got some new peaks over here. I'm just going to put this into the data processing peak ID, and we can see what we've got. Now we can actually see the copper and the aluminium present that's in the coin, as expected. Sadly, there isn't any gold in this coin, but never mind. It's only $1. You can see the carbon peak is a lot smaller. However, there's still a big oxygen peak, and that's just because the metal is oxidized. If we were to scan this or do the etch for quite a few minutes longer at a higher power, we would probably remove the oxide layer and we'd just get the pure metal. And that's how we do the etch of the sample. So now that the data acquisition is finished, we can now turn off the instrument and remove the sample bar and take it out of the chamber. So first of all, we go to Instrument, right click, press Turn Off. And also in the Prepare Instrument box, I've just pressed Off. It's important that you only press it once. If you press it a few times, it will do the off cycle, then it will do it again and again and again. So just once, then you have to wait about 30 seconds, and then the instrument engages, and then you can see it happening. This is the GCIS turning off. And then just to check that the X-rays are off, what we can do, we can left click here, and it gives us information on the system. X-rays are off because this box is grey. The charge neutralizer is on, it's turning off, and the analyzer is also turning off as well. So now the instrument has turned off, we can remove the sample bar from the chamber, put it back into the FlexiLock, vent the FlexiLock, and then remove our sample bar. Before you move the sample back into the chamber, you just have to check that the pressure in the FlexiLock is okay, it's low enough to open it up to add the sample bar into. So as you can see now, the pressure in the FlexiLock is below where it should be, it's in the -8s, and so we can now remove the sample bar from the sac into the FlexiLock. I'm just going to go to the sample loader tab, and you see now there are no sample bars in the FlexiLock. So I'm just going to move the sample bar into one of these. So we'll pick number 2, and I'll press transfer the sample holder from the stage to the empty magazine slot. So now the sample bar will be removed from the sample stage, go into the magazine slot, and then we can remove the sample, we can vent the chamber. Firstly, the sample bar gets calibrated. When it's calibrated, the gate valve will open, and then the magazine will come in and the sample bar will be dropped into place onto that, and then we can remove it and vent the chamber. So now that the sample is back in the FlexiLock, it's time to vent the chamber. So before we vent the chamber, we've just got to do a check to make sure that the Flexilock gate valve is closed. So this is very important. We don't want to vent the sac as well. It should be closed. If it's not, just come and grab me. Do not vent the chamber. Before you vent the chamber, you've just got to slightly unscrew the Flexilock door just to prevent any pressure build-up. Loosen it a little bit. That way when the pressure builds up, it won't damage the instrument. And we don't pull this off all the way, just in case the pressure is a little bit higher. We don't want the door to swing open and hurt us. In the sample loader window, we then press vent, and that will start the process of venting the chamber. The Flexilock turbo pump will slow down, the Flexilock backing valve will close, and then once the turbo pump is slowed down, dry nitrogen will go into the Flexilock. It will reach atmospheric pressure.